Okay, so what topic are we talking about here? So we're going to talk about application. So we're going to talk about divisibility and primes. Okay, so let's talk about it. So again, the definitions play a fundamental role here. We should understand what the definition is, and we can only apply these definitions because let's first look at the division definition. So again, our space, what we are talking about is space of integers. When uh, we talk about divisibility and primes. Okay, we are not interested in 1.1. We are not interested in 2/3. We are not interested in those numbers. Our interest lies only in the space of integers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah blah blah, 0, and on the other side -1, -2, -6. So this is the universe we are going to play with. All right. Okay. So let A and B be integers. We say A divides B. And the notation for that is you put A like that. So this is a notation for A divides B. All right. So what is the meaning of A divides B? Again, this is a definition. So whenever we are proving any result, we must use this definition. So what does it mean by A divides B? Again, we don't want to divide by 0. So A and B belong to C. This is a short way of saying that they are integers. And A is not 0. Yeah. Then we say A divides B. The notation for it is that A and then there's a vertical line B. If there exists K, again an integer, K an integer, such that AK equals to. So this is the definition of A dividing B. All right. And we must always use this definition. All right. So let's see. So let's ask few questions. Does say 3 divides 4? Sorry, not 4, but let's say 42. Yeah. So this is the question. Or in other terms, we can ask, does 3 divides 42? And the answer is yes. Why? Why the answer is yes? The answer is yes. Why? Because now we have to produce a K. So what is that K? K is 1 and then 4. So 14, right? So because K equals to 14 is such that 3 times 14 equals to what? 42. Okay. So let me just make it clear. We have, this is my A, this is my B, and this is a job of K. All right. So this is what it means by A divides B. Yeah. Is that clear? Yeah. You can't say, this is not a good justification. 4 by 3 equals to 14. No, such things don't exist for us. Yeah. All right. So we have, again, A divides B. If there is some number K, we don't care what that number is, some integer K, unless we want to prove something concretely, if there is some integer K such that AK equals to B. All right. So this is the idea behind divisibility. Now, same thing can be said in many different ways. One is if A divides B is same as saying A is a factor of B. So it's same as saying A is a factor of B, or it's same as saying B is a multiple of A. Okay. So any of these things basically mean the same thing. Okay. That A divides B. All right. Is that idea clear? Now, so these are some results we need to prove. So let's try to prove these results. Now, let A, B, C be integers. We want to prove that if A divides B and A divides C, then A divides B plus C. And then we want to prove, so these are the three results, A divides B and A divides BC, then, sorry, A divides B, then A divides BC for any integer C. And then if A divides B and B divides C, that means A divides C. All right, so let's look at these results. How do we prove it? Again, we will prove it based on what? Just one result, which is what the definition of divisibility, which is what A divides B is same as saying there exists an integer K such that AK equals to B. Does that make sense? Let's proceed now. Problem 1. So let's prove this. So A divides B and A divides C. Then what? A divides B plus C. So how do we prove it? Now, A divides B implies what? There exists K. I'm going to use K1, an integer. So I will use K1 belongs to Z. If you don't like this symbolism, you can say K1, an integer, such that what happens? Such that AK1 is B. All right. This is the meaning of the statement A divides B. Now let's look at the second statement. What is the second statement? So A divides C. So A also divides C, that is given to us. This implies there exists K2 belonging to Z such that what? AK2 equals to C. Yeah. Now we want to make a statement about B plus C. So let's check what is B plus C. In that case, we get B plus C is equal to what? B plus C is AK1, AK2. Take A common, we get A, K1 plus K2. Yeah. And now we are going to replace this by what? This is same as AK, where K belongs to what? Where K equals to K1 plus K2 belongs to Z, right? This is true, right? If you take one integer and take another integer, you add them, you get an integer. So this implies what? This implies A divides B plus C. So you have proved the first result, which is what? If A divides B and A divides C, then A divides B plus C. Yeah, does that make sense, right? So this is how you will go about proving it. No fraction writing, no bracket writing, nothing else. This is the way. Why? Because in mathematics, it's all about, you start with a definition and then you use the definition to basically make a proof of a theorem. Yeah, it's all definition based. Sometimes it happens in mathematics that different textbook will have different definitions for the same thing. They are equivalent, but the idea is that one starts with the definition, proves this thing. So the first is a definition, second is a result. And in some book, you take the second one as a definition and prove the first thing. So the first thing becomes result. Is that okay? But you can't take both of them to be true. Why? Because the idea is you start with a statement, a definition, and then based on that, you prove things. Is that clear? Yeah. So this is how it goes. Now, can we try to do problem basically B? So let me call this a problem A, statement B. Let's try to prove statement B. So B. Let's try to see the B. Okay. So again, the starting point is if A divides B, that means what? Since A divides B, we're given, since A divides B, this implies there exists an integer K in Z such that AK equals to B. All right. Now you want to make a statement about BC, that A divides BC. So let's see how BC looks like. So we get BC equals to what? Multiply both sides by C, you get BC equals to AKC. Then you have A times KC equals to BC, right? Then you say, okay, well, since KC belongs to Z, right? You don't need to argue that, but I mean, a proper way would be K is an integer, C is an integer, you multiply them, you get an integer. Yeah. So this is a property of, nice property of integers. You say, this is an obvious property. Why do I need to write this down? Note, if you're playing with irrational numbers, square root of 2 times square root of 2 is not irrational anymore. It becomes rational. Yeah. So things like this must be spelled out, at least in the game we are playing. Yeah. So we can say since KC belongs to C, this implies what? A divides BC. We're done. So this is the proof of the result that if A divides B, then A will divide BC for any, yeah, yeah, for any C. Now let's look at the problem C. Problem C, proof of C. Now A divides B. This implies what? There exists C belonging to Z such that, or sorry, let's use K1, huh? Because K1 belongs to Z such that A K1 equals to B. Yeah. Similarly, for the second one, B divides C. This means there exists K2 belonging to Z such that B K2 equals to what? C. Yeah, do you agree with that? This is again coming from the definition of divisibility. A divides C, that means there is some K such that AK1 is B. B divides C such that means there exists some K2 in Z such that BK2 is C. Now we want to show that A divides C. All right. Now already you should think about it. You're not going to stumble upon the solution. You should think about it. What does it mean? I want to write C equals to some multiple of A, right? So let's start with that. So we get what? So here we get C equals to BK2. But what is B? From the earlier one, we get B is same as AK1, K2. This will give me A times K1, K2. Yeah, isn't it? So now here I should argue that, hey, K1, K2 belongs to Z. Since K1, K2 is an integer, this implies what? A divides. Okay, so next important result is about prime. So again, we are defining a bunch of things. So what is a prime number? So a prime number is a number. So, well, what kind of numbers qualify to be prime? Okay, so again, when we talk about prime number, we only restrict ourselves to positive integers greater than 1. So we say a positive integer greater than 1 is prime if and only if the only positive factors of P are what? 1 and P. Okay, then such a number is called prime. Is that okay? So is 2 a prime? The answer is yes. Why? Because 1 and 2 are only numbers that divide 2. Okay. Now, what about 1? Is 1 a prime? Why not? Yeah, it doesn't fit the definition because we don't talk about prime. We can say prime numbers are only defined for numbers, integers, basically bigger than 1. All right. So now, so this is how we can talk about. So basically, this is a definition of prime. Now, to play with numbers properly, so first of all, if a number is not prime, then we call such a number as composite number. Yeah. So an integer. So otherwise it's called what? Composite. Composite example would be, example is 6 is basically is composite. Yeah. What is the justification for that? Because 2, which is not equal to 1 and not equal to 6, divides what? Divides 6, isn't it? Yeah. It basically, so again, the definition is 1 or P are the only integers which divide that number, so it becomes prime. So if you want to show that something is not prime, you have to produce an example of a number which is not 1, not itself, but divides that number. That is a justification for basically what? For basically a number being composite. Okay. Later on, of course, we'll see the results saying, oh, if it is product of more than 2 primes, then it's not composite. But that is an outcome. That is not a definition. See? Yeah. Again, I'm emphasizing on this fact a lot, but I hope it becomes clear to you. So now, There is a fundamental theorem of arithmetic. It's a very powerful result. Actually, a lot of mathematical theories come out of this. So it very straightforward though. It says the following. If you take a positive integer, it can be written as product of powers of prime. What do I mean by that? Let's take a number. Let's take 24. Yeah. So the fundamental theorem of arithmetic says that you can write it as powers of prime, product of powers of prime. So product of prime. So primes are basically say 2 to the power 3 and say 3, right? 2 to the power 3 is 8, 3 8s are 24, right? Yeah. So it says that 24 or any number, actually, every positive integer can be uniquely written as product of primes, where the primes can be written in increasing order. What do I mean by that? See, 24 is also same as 2 times 3 times 2 times 2, isn't it? I can write it in whatever order I want. Yeah. But prime fundamental theorem of arithmetic says, no, I can write it in a way that the primes are in the increasing order of the size. Yeah. Why would somebody need such a result? Because it gives a nice structure to this decomposition in terms of prime powers. It's a very, very powerful result, right? Now, suppose I want to check a number is prime or not. Yeah. How would I check it? Yeah. So suppose I give you a number, say, let's say 101. And I want to check if 101 is 101, right? Well, one naive way would be to start with basically from 2 all the way to 101, actually 100, and check if there is something other than, well, 1 and 101 are already excluded. So check if any number in between divides that number. Is that okay? Yeah. You can say, oh, ask questions. Does 2 divides 101? Question 3 divides 101, and so on. Go all the way till 100 divides 101, and ask this question, right? And then when you see that none of them is true, then we declare that it's prime. If one of them is true, that one of these numbers divided, then it's composite, right? Does that make sense? Now we don't need to go that far. Yeah. The result is you actually just need to go until square root of n. So to check 101 is prime, we need to check only until square root of 101. Again, this is not an integer, so this is roughly like what? 10. So you need to check all the way till 10. All right. And in fact, you don't even need to check all the way till 10. You only need to check for the prime numbers from 1 to 10. Actually, from 2 to 10. Okay. So let's see. Does 2 divides 101? No. 3 divides 101? No. You know the divisibility test, right? For 3. If you add the digits and the sum of the digits is divisible by 3, then the number is divisible by 3. Yeah. You know that result, right? Yeah, that's a quick way to check if a number is divisible by 3 or not. Let's take, for example, 153921. Is it divisible by 3? You just add this up. So 6 plus 3, 9, 9 plus 9, 18, 18 plus 2, 18 plus 3 is 21. Yeah, so you get, when you add the digits, you get 21. Add again 2 plus 1, you get what? 3. Is 3 divisible by 3? The answer is yes. So this number is divisible by 3. That is the fastest way of checking if a number is divisible by 3. So same thing works for 9 as well. And then basically you can check out for 9. The same thing happens. So you add all the digits up. Yeah. If the sum of the digits you get is divisible by 9, then the number is divisible by 9. Otherwise, the number is not divisible by 9. Let me give an example. 81. Yeah. Is 81 divisible by 9? The answer is, well, we know that 9 times 9 is 81, but the easy way to check is do 8 plus 1. You get what? 9. Does 9 divides 9? The answer is yes. So therefore, 81 is divisible by 9. This is how you check whether the number is divisible by 9. This only works for 3 and 9. Let's look at another example, and maybe this time it will make sense. Let's take a number, say 182. I'll say 21. Okay. Is this divisible by 3? Yeah. So what you do is you sum the numbers up. You get what? 1 plus 8 plus 2 plus 1. What is that number? So we get 12. So then you ask the question: is 12 divisible by 3? The answer is yes. So does 3 divides 12? The answer is yes. Therefore, 1821 is divisible by 3. Okay. This is a quick way of checking it. All right. The proof is beyond your scope at the moment, but if you're really interested, I can actually discuss the proof during the break time with you. Okay. But otherwise, we can just quickly take this at the face value. That's one. Secondly, you can quickly also say that this number is not divisible by 9, right? Why? Because when you add the digits, you got 12, and 12 is not divisible by 9. Therefore, this number is not divisible by 9. So these are the quick ways of checking whether the number is divisible by 3. 3 or basically 3 does it. So this is a way we can check with 3 or 9. That's all. All right. Okay. So I said, when I say it's only working for 3 and 9, that means only works for 3 and 9. Yeah, we cannot ask questions like, does it work for 4 or does it work for 9 or 11 or 20 or 41? No. When we have already made a statement, our statement is that it's only working for these two. So that means it does not work for anything else. Does that make sense? Yeah. Yeah. So 2 divides, so 3 divides does not divide it. Next, what are the next prime to check? 5. 5 does not divide it. Well, the next one is what? 7. So 7 does not divide it. And then we have exhausted all the primes starting from 2 to 10, the prime numbers in between. So we are done. So see the beauty of this, right? I mean, like 101 is such a big number, but you only need to check until this. All right. So what is the proof of this? I can quickly discuss the proof of it. Let's take a number 101. Suppose I have a divisor of it, AB. Yeah. Now look at this number A and B, these two numbers. Yeah. Now, both of them have to be less than equal to square root of n. Yeah. If yes, do you agree? I mean, if A is greater than square root of n, and if B is greater than square root of n, then AB is going to be greater than what? And you're checking for bigger number. Yeah. So all you need to do is you need to check for numbers between 1 to square root of n. And not only that, because everything has a prime factor because of the fundamental theorem of arithmetic, if you want to think that way. So all you need to do is see if there is a prime number from 0 to square root of n to decide this. Yeah. So this is how your life becomes easy doing computations. Okay. So the next thing we want to talk about is division algorithm. So what is the division algorithm? Division algorithm is basically it's just showing you the way of division, really. Okay, and it's making it this statement of division precise. So what does division algorithm says? Let me just illustrate it for you. Let's take, suppose you have a number, say, let's say 11, and you're dividing 11 by 3. Let me do this arithmetic here. So we have 11, and we are dividing 11 by 3. Okay. So we have 11 divided by 3. So when we do this division, how does it go? So 3 ones are no, 3 threes are 9. The remainder is 2. And then we ask this question to ourselves, do we stop here? And the answer is yes, we stop here, right? Suppose I have some another number, say 1 here again. Then the question is, oh, sorry, let me just take 2. Yeah. And then when we get to this point, when we divide, we get 9, and then we are left with 2, and then we get 2 below here. And the question is, do we stop here? And the answer is no, of course, we keep on going, right? Then we say, okay, 3 7s are 21, and then we have 1. So this is my remainder. This is my quotient. These are the names associated with it. So remainders will be denoted by, say, let's say notation R. This is a quotient, which is notation is Q. This is my, this, sorry, not this is quotient, this is divisor, my bad. Sorry. So we have 3 is the divisor, right? The one you're dividing with. What you're dividing with, this is my dividend, and this is my quotient. So these are the names of the actors in a division algorithm. Okay, yeah. So again, the idea is you keep on doing the division algorithm. You keep on doing this until your remainder is less than what? Divisor or equal to 0. Is that okay? So that is what the division algorithm is. So if I want to write this in terms of letters, so suppose that this is R, this is mine. This is basically, say, Q. Suppose I have this to be, this is my D. All I'm saying is, and this is my A, I'm saying is A equals to this dividend. If I divide it with Q, I get some, or if I divide with D, I'm going to interchange it, okay? So the starting point of this is the following. I start with A, and I'm dividing it by number D. Okay, so I'm going to divide A by D. All right, sorry, there was a little bit of mix up there because I was not using the right variable for the object, because I want to have the same expression as my lecture notes. Okay, but you can take whatever variables you want for whatever you want to. Suppose I have A and I divide by D. Yeah, what does division algorithm says? Division algorithm says then I can find, then there exists a number Q and R such that my A becomes QD plus R. Yeah. With extra condition that my R is what? R is greater than equal to 0, but less than what? D. Yeah. Well, why? Because, well, if it is not less than D, then we can continue the division algorithm. Yeah. So this is the division algorithm. All right. So the division algorithm says that if I take A and I divide it by D, then I can find some number Q, which is my quotient, some number R, remainder, such that A equals to QD plus R, where Q is some integer and R has to be less than D. And it can be 0 as well, between 0 and